Hello, I'm here with another video, this time related to statically indeterminate structures. So we have this bar AD, which is attached to two rods, CE and DF here, and then being pulled at point A by a 10 kip load. Our objective here for this problem is to find the tension or forces that are developed in bar CE and bar DF. Now we know obviously they have different length, but also they have different diameters, so they're going to have different cross-sectional areas. So we know that bar CE has a diameter of 1/2 inch. And let's say bar DF has a larger diameter, so it's 3/4 of an inch. But let's say both bars are made of the same material. They're made of aluminum with a modulus of elasticity of about 10.1 times 10 to the 6 psi. So both bars CE and DF are made of the same material. Okay, our objective, besides finding force in member or rod CE and force in member DF, is also to find how much deflection point A is going to have. So I'm going to call that delta A. So that would be deflection of A. What would be the vertical deflection of point A? And of course, you'll see later on that this is really small deflection. Okay, so how are we going to approach this problem? And the question is, why we say that this is a statically indeterminate? First, let me define what do we call a statically indeterminate system or structure. Whenever the number of unknown reactions in a problem is more than the number of available equilibrium or useful equilibrium equations, the problem becomes a statically indeterminate. So let's draw a free body diagram for this system. So we know that we have a pin connection at B, so we're going to have the typical BX, BY. Clearly we have force, tensile force developed in this member, FCE, and also tensile force developed in this member FDF. Actually, it turns out that actually these would be acting the other way, as we'll see. Actually, would be in tension. So we'll see. Obviously, point C is going to move up, and point D is going to move up. But in any case, you notice that there are actually 4 unknowns here now. 4 unknowns. Clearly, the unknowns are what? BX, BY, the forcing member CE, and the forcing member DF. But there are only 3 equations, 3 equilibrium equations. What are the 3 equilibrium equations? Sum of the forces in X equals 0, sum of the forces in Y equals 0, and sum of the moment equals 0 for any 2-dimensional rigid body equilibrium. So definitely this system is a statically indeterminate. So if this problem was presented to you in a typical statics course, you won't be able to actually solve for all the unknowns. So you'll see how we can actually overcome that. So let me show you that. One useful equation that we're going to use here is sum of the moment. And the best point to take moment about it would be point B. So let's go ahead and take moment about B. We'll take counterclockwise to be positive. We notice that the moment of FCE about B would be FCE times, and we can keep these in inches, by the way. There's no reason to change them. 12 inch. That's going negative direction. Then the forcing, the moment of forcing member DF also going to be 20 times 20, and then on the other side we have the moment of the 10 kip applied load, that's going to go in the positive direction. 10 times 18 equals 0. So actually, if we clean up this equation, we get a 12 FCE plus a 20 FDF. We'll take it to this 180 to the other, so we get 180. So here's one equation with two unknowns. Not a good idea to use the sum of the forces in y equals 0 because you introduce another unknown, by. So now, if I could somehow find the relation between the two forces, the two unknown forces, then I'll be all set. I can solve this problem. That relation actually comes from the geometry. So if the bar initially is like this, is straight and horizontal, and this is the pivot point here, point B, how would this bar deflect or deform? So it would deform like this. Of course, I'm exaggerating here. So this is the deflection of point A. That's what we're trying to find here. This would be actually the extension of point C. I'll call it delta C. And this would be delta D. All right. So now, using the geometry, you could see that delta C divided by this distance, which is 12, should be the same as delta D divided by this distance. Basically, using similar triangles, that's 20 inches. So this relation that delta C over 12 is the same as delta D over 20. So basically, if you rearrange this equation, delta C becomes 0.6 of delta D. And now, how are these deformation, elastic deformation, delta C and delta D are related to the forces? Well, very easily. Delta for axially loaded member is equal to PL over EA. So delta C would be the force in member CE times the length of the member CE divided by E. Now, material is the same, but the area is different. So this must be equal to 0.6 of what? Delta D. What's delta D? Force in bar DF times the length of DF divided by E and the area of DF. Of course, the only term that we can get rid of here is E. It's made of the same material. If we go ahead and plug in the numbers here, and let me try to see if I can fit it right here, and then we go to the next page. So we have an FCE times the length of FCE, which is, as you could see, is 24 inches, divided by E is already gone. This is pi over 4. I'm trying to calculate the area. So this is the ½ inch squared. And over there we have 0.6 of now delta D, which is FDF times the length of it, which is, as you could see, is 30 inches, divided by area. Of course, this has a larger cross-sectional area, 3/4 in diameter. If you clean this up, you see actually pi over 4 and pi over 4 cancel out. The relation that I get is that FCE becomes a third of, actually 1/3 or 0.33 of FDF. And this is the second equation that I can now use to solve the problem. So now let me go to the next page and show you that we have two equations now. We have 12 FCE plus 20 FDF equal 180. So this is one equation, and I just found, based on deformations, that FCE is 0.33 or 1/3 of FDF. So just a simple substitution here of, over here, you solve for FDF and FCE. Here they are. FDF should come out to be, if you keep it in kip, which was the case, 7.5 kip, and FCE, remember, a third of this, so it would be 2.5 kip. And actually, this implies that actually BY actually becomes 0 because these two, BY becomes 20 because we have a 10 here and 10 here, so it would be 20. But actually, we don't care about BY. Now, the next question is, how do we find this delta A? Also, from the geometry, you could see that delta A over 18 here, right, is also the same as what? Delta D, for example, or delta B, doesn't matter, delta B over 12. So you could see that delta A is going to be 4/3 of delta B. So let me move over here and say, oh, delta A is going to be 4/3 of delta B. And what is delta B? Now we can actually go ahead and calculate delta B. Delta B is going to be the forcing member. So we're looking for delta. I'm sorry. This is delta C here. Sorry for that. We don't have any delta B. So let's go back here and put delta C here. So delta C is what? FCE times the length of CE divided by E times A. So just a quick plug-in. Keep in mind that FCE came out to be 2.5 kip. That's 2,500 pound. Kip is 1,000 pound. The length of this guy going back is 24 inch. E is 10.1 times 10 to the 6 psi. So units are all consistent. And then the area is pi over 4 ½ inch in diameter squared. So if we work this out, we should get a delta A of about 0.0454 inch. So you see how small this number is going to be. Sorry that this video went longer than 10 minutes. My intention is always to have videos lower than 10 minutes, but I guess this was a more involved problem. As always, thank you for watching and listening, and looking forward to do more videos for you. Thanks again.